Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets review for August of 2022. And in contrast to last month, there were several major new planet discoveries in August. Probably the headline one was TOI 1452b, a new super-Earth in a quote-unquote temperate orbit around an M-dwarf. So this is a red dwarf planet. I've talked about them several times before. Probably looks something like this. Probably with less atmosphere streaming away. This is just a stock illustration. They've got decent measurements of its mass and radius, and that puts it kind of on the border between Earth-like and Neptune-like. Earth-like is a mix of rock and iron, Neptune-like has a thick hydrogen atmosphere. This is kind of in the middle, which suggests it could be a water world, a planet that does not have a thick hydrogen atmosphere, but does have a large fraction of its mass made of water. And they say it's temperate, which means potentially Earth-like in temperature, but its equilibrium temperature is 326 Kelvin, which is 53 degrees Celsius, and Earth's equilibrium temperature, which is the temperature before the greenhouse effect, is something like minus 18 Celsius. So this planet is hot enough that it could be a runaway greenhouse Venus-like environment, but it could also be habitable. There's differing opinions on how inevitable the runaway greenhouse is at those temperatures. But the most important thing is that this is a top-tier candidate for JWST follow-up observations to actually characterize its atmosphere, and then of course we'd have a better idea of what it's made of and what its climate is like. And it's not quite on TRAPPIST-1 level, but it is up there with well-known planets like LHS 1140b and K218b. If you're familiar with the exoplanet field, those are names that will mean something to you. So this is very exciting for the characterization of its atmosphere that we will hopefully get next year. Next up, we have another interesting planet, which is another test planet, TOI 2196b, a rare planet in the hot Neptune desert transiting a G-dwarf. And the Neptune desert is something I've talked about a few times before. If you look at the radius versus temperature plot of known planets, for very hot planets, you see quite a few that are Jupiter-sized and quite a few that are Earth-sized and very few that are in between, and we call that the hot Neptune desert. But you do see a few planets in there, and this is one of them. You can see in the plot here, there's actually several other planets clustered around it, but not much in this whole region. Composition-wise, it's a pretty standard hot Neptune, estimated to be about 1% hydrogen by mass. That part's not that remarkable, except that it's so hot. I just thought this graph was interesting, because this is mass-radius relation for a given composition, and that composition is 0.3 to 1% hydrogen at 2000 Kelvin, which is hot and borderline ultra-hot. And I just thought this was interesting because I hadn't seen this before. The pink strip is the region we're talking about, and you can see it's around 4 Earth radii, so about Neptune-sized, down to about 10 Earth masses, and then it takes a sharp turn and goes straight up, well past Jupiter radius, and that basically means there is no solution to the equations of planetary structure. At that temperature, the planet simply cannot hold on to an atmosphere. And that may seem obvious, but I had not seen it illustrated that way before, so I thought that was interesting. A third interesting planet, this is a microlensing planet from the Ogle survey, and it is interesting because it is a super Jupiter planet orbiting an M-dwarf, and that is quite rare. Jupiter mass planets are rare around M-dwarfs. So it'll probably look something like this, and it is 3 times the mass of Jupiter, and it's orbiting a star it's not super small, but 0.42 solar masses is fairly small to be having a Jupiter-sized planet. Its mass ratio is close to 100 to 1, which if you compare with our solar system, the Sun to Jupiter is 1,000 to 1. And it's also on a fairly long orbit, 2.18 AU, which around a star this size is going to be about Saturn temperature. And with these parameters for this object, I have to wonder if it's actually on the tail end of the brown dwarf distribution, because we're pretty sure that the stellar and brown dwarf formation sequence does extend down into the super Jupiter mass planets. So these kinds of discoveries are worth keeping an eye on to get a better idea of what the limits of planets are. There was also one interesting paper about planet populations, revising properties of planet host binary systems. I think that may be a typo. Apparent near-Earth analog planets in binaries are often sub-Neptunes. And this is getting into the two different types of planets that you'll find in binary star systems. There are the S-type planets, which orbit just one of the two stars in a binary, and then there are the P-type planets, which are also known as circumbinary planets, where the planet orbits both stars at once. And the P-type systems are more famous. Tatooine in Star Wars is a P-type system, but this paper is actually about the S-type systems, where the planet is orbiting just one star. And this is tricky when you're looking at transits, and radial velocities for that matter, because there are two stars, and there's not really a good way to tell which star the planet orbits, unless the stars themselves eclipse each other. So you see a dip in the light from the combined stellar spectra, but unless you can take really good spectra to separate out the two components, you're not really sure which star the planet orbits, and that leads to more uncertainty. And what this team did is they looked at a number of Earth-like planet candidates that were in S-type orbits in binary star systems, and reanalyzed the observations and did new observations of the stars, some of which could be resolved in a higher magnification telescope. Kepler and TESS are deliberately defocused a little bit because it's easier to measure the amount of light that way. So a higher resolution telescope can resolve some of these stars, but not necessarily tell which star the planet orbits. But using these better stellar parameters, they recalculated the radii based on both possible host stars. So in this plot, on the left you have arrows pointing from the original Kepler radii to what they now think the radius is if the planet orbits the primary, that's the larger star. And on the right you have what they think the radii are if the planet orbits the secondary or smaller star. And in both cases, they got significantly larger radii than Kepler measured. And this means that these apparent Earth-like candidates are mostly mini-Neptunes that are larger than 2 Earth radii. So that revises down the number of potential Earth-like planets in binary systems quite a bit. Some of them are still in that range, but not as many. And that is something that planet hunters will have to watch out for going forward. Several interesting papers about planet formation. First, we have the evolution of protoplanetary disk radii and disk masses in star-forming regions. And this is looking at various young star clusters and star-forming regions. ONC is the Orion Nebula, for example. And they measured the distribution of protoplanetary disk sizes and estimated masses in each of these clusters. And you can see the cumulative distribution function. So the midpoint of that curve is the radius where half of the disks are larger than that and half are smaller. And you can see in Orion, that's at about 10 AU. And in Lupus, it's at more like 100. So there's this spread, and they ran the clock backward and forward in simulations to model what the disk radius and disk mass look like at different times. And actually the disk spreads out over time as it loses mass, because some of the mass accretes onto the star, but some of the mass also escapes from the system. So older disks are significantly larger, but less dense. And that's just an interesting result that will help drive future planet formation simulations. Next, we have trapping sub-Neptunes similar to TOI 216b at the inner disk rim. The TOI number isn't that important. the important thing is this is modeling migration of mini Neptune-type planets and fully Neptune-type planets. And this is related to what I talked about earlier with the Neptune desert. There's this region close to the star where there are no Neptune-sized planets. And the standard line is that it's due to photoevaporation. This region is very hot because it's very close to the star, and the atmosphere just evaporates away. The trouble is, if you try to model that in a simulation, it doesn't quite line up. The edges of the desert are not quite where they should be. So the next theory is that it's some quirk of planet formation that Neptune-sized planets just don't get there. One idea is that planets migrate inward due to gravitational interactions with the disk, and for these intermediate masses, Neptune-sized planets, the migration stalls at about 0.1 AU. So they just don't get in that far. And they did simulations of this with a fancy magnetohydrodynamic code, and they got results where this mechanism works some of the time. Here's the surface density and temperature of the disk. So this is basically the disk model they're using. And the result was this. So on the left, this is the disk unwound into a square. So to the left is toward the star, and up and down are around the circle, just unbent into a straight line. And this is showing surface density, and there's this spiral density wave going through about where the planet should be. And on the right, we have planet mass versus radial distance, and the color is torque. And torque, if you know intro physics, is what determines the migration rate. If torque is negative, the planet migrates toward the star. If it's positive, it migrates away from the star. And you can see there's this region of positive torque that affects planets smaller than Neptune, smaller than 20 Earth masses, at about 0.1 AU. So a planet that enters that region stalls, whereas a more massive planet keeps migrating in to become a hot Jupiter. So these competing models of both the radius valley, which we'll come back to a little later, and the Neptune desert are very interesting because there's several different things that might be causing it, not all of which are the most intuitive ones. And it remains to be seen which, if any of them, or maybe all of them, are really responsible for the distribution of planets we observe. A couple other papers about disks, or rather belts, which are closely related. Eccentric debris belts reveal the dynamical history of the companion exoplanet. And this is about dust and debris belts, kind of like the asteroid belt and the Kuiper belt, but generally back a little closer to formation. And some of them we observe, like Fomalhaut here, have dust rings or debris rings that are very conspicuously off-center. And this is unusual because the asteroid belt and the Kuiper belt in our solar system are very much circular. They're very broad and more donut-shaped, but they are circular. Now, a planet with an eccentric orbit could create an eccentric debris belt. And there are gravitational arguments for that, kind of similar to the proposed mechanism for Planet 9 creating a group of objects that are lined up on one side of the sun. The thing is, when we look at these eccentric debris belts around other stars, they're narrower than we expect. We expect eccentric planets to produce belts that are off-center, eccentric themselves, but very wide, and we're not seeing that. So this study looked at different ways to produce a narrow belt in simulations, and they found two different processes. One is that interactions with the gas disk, which creates drag and tends to create what we call laminar flow, where everything just kind of orbits together without getting in each other's way. That could produce a narrower belt. And the other is if the planet and the belt started out circular, but then the planet was kicked into a more eccentric orbit by planet-planet scattering. And that would scatter a lot of the debris, but a lot of it would settle into a new eccentric belt that would be narrower than if it just formed that way. So that definitely needs further study to see if one of those scenarios works better than the other, or if they make predictions that maybe observations could distinguish them. But that's another piece of the puzzle that's important for planet formation to understand the distribution we see. Now this one is not strictly about exoplanets, but I thought it was worth including. It's also about belts and disks and what happens if they're misaligned. And it has to do with the interstellar asteroids we've observed. In the past few years, we've observed 2 interstellar asteroids, or comets. The first was famously Oumuamua, and the second was Borisov. And we've also seen some interstellar meteors hitting the atmosphere. But the interesting thing is that those 2 objects are more than we expected to see for how long and how widely we've been looking. And we need something of an explanation for how that happened. And one theory is another way of producing an off-center debris disk, although probably a wider one in this case, is to have a binary star system. So binaries are coming back again too. A binary star system could create an eccentric or off-center disk, and just like I talked about laminar flow from gas drag, in an eccentric disk or belt, things are generally going to be less laminar. You're going to have orbits crossing each other at steeper angles and objects hitting each other at higher relative speeds, and that creates fragments from collisions, some of which can fly off at high speeds into interstellar space. And an eccentric belt, for several gravitational reasons, can produce quite a few more of these interstellar asteroids. And in fact, the authors calculated that about 60% of binary stars will lose most of their planet-forming material to these collisions. And they have some graphs here of their simulations, looking at binary stars with different orbital inclinations and eccentricities, and seeing how they would affect the disk, the velocity distribution of particles produced as a function of distance from the stars, and on the right, where they're plotting energy, anything above the black dashed line is going to escape to interstellar space. So they've found some stellar system models where they would lose a lot of material to interstellar space, potentially becoming the interstellar asteroids that we've observed. Moving on, there were several interesting papers about planetary atmospheres. The headline paper here is a JWST result of what I'm pretty sure is the first conclusive detection of carbon dioxide in an exoplanet atmosphere. This is on WASP-39b, which is a hot Saturn. And carbon dioxide is important because it's an indicator of overall metallicity. It's a molecule that doesn't have hydrogen, so it's a stronger indicator than something like water or methane of how much non-hydrogen stuff there is in a planet, which makes it an important tracer for planet formation processes. And we found carbon monoxide in planets before, but not carbon dioxide yet, not conclusively, and the chemistry for that is different, so it's important to get a different perspective on the range of possibilities. And JWST continues to deliver. The carbon dioxide detection for WASP-39b was 26 sigma, which means 26 times the measurement error. And for comparison, when the particle physicists discovered the Higgs boson, they announced that with a 5 sigma detection. So this is a really good quality detection, and I'm expecting more good results like that from JWST in the future. The result was not that remarkable. They found a similar metal enrichment to Saturn, but that they're able to take these observations now is very important. Then we have what I'm pretty sure is only the second non-detection of an atmosphere on GJ1252b. This is an ultra-short period super-Earth. It orbits its star in only 12 hours. And because its star is an M-dwarf, it's not ultra-hot, but it is very hot. Hot enough that its surface is probably molten. And because it's so hot, the day side radiates in infrared. And when the planet passes behind its star, that infrared radiation from the planet is blocked, and we can see a noticeable dip in the star's light. That's called the secondary eclipse. And Kepler and TESS can see that in a lot of cases, in addition to the transit. And if we measure precisely how much the star plus planet brightness changes during the secondary eclipse, compared with the transit, we can get a good idea of how hot the day side is compared with the night side, and how much redistribution of heat there is from the day side to the night side, because heat redistribution will mainly be due to an atmosphere. And a couple years ago, they did this for a cooler planet, LHS 3844b, and found no atmosphere. And now for GJ 1252b, which is hotter, they also found no atmosphere. Now there's an asterisk to that, which is no atmosphere really means less than 1 bar, which is 1 Earth atmosphere. And they've got a decent 1 sigma detection, which is sort of the minimum standard, that they're pretty sure there is no atmosphere more than 1 bar, 2 sigma for 10 bars on this planet. So, honestly, I'm not really sure what to do with these measurements that say no atmosphere, but no atmosphere is really an upper limit of a few times as much atmosphere as Earth has. But it's a problem they're working on, and hopefully, especially with JWST, they'll continue to improve their results there. More on the theory side, I've been waiting for a new paper on this topic to come out. I was sure there were people working on it, I just hadn't seen one in a while. Signatures of impact-driven atmospheric loss in large ensembles of exoplanets. And this is related to something I've talked about in several previous reviews. Atmosphere loss from super-Earths and mini-Neptunes. And there's sort of these two competing models, photoevaporation, where the atmosphere is lost due to irradiation from the star, and core-powered mass loss, which is the atmosphere evaporating away due to the heat of formation of the planet. But there is a third mechanism that can drive away the atmosphere, and that is giant impacts. And giant generally means something like Moon or Mars-sized, not just asteroid-sized. An impact on that scale can blow away a large part of the atmosphere just because it's hitting the planet really hard. And importantly, for low mass and especially low temperature planets like Earth, there are models that suggest that giant impacts are the dominant mass loss process. So this team ran simulations of impact-driven mass loss to predict population-level trends in transiting planets. And this is something I've seen done several times for photoevaporation versus core-powered mass loss to see if they result in different profiles of exoplanets. This is the first one I can remember seeing doing the same for impacts. And they found some very interesting results. This is the radius period diagram. It's very idealized because it's from a simulated planet population. The radius valley is not nearly as clean as either of these pictures in actual observations. But the important thing is, giant impacts produce a narrower and less empty radius valley than photoevaporation. If impacts are dominant in the planet population at large, we would expect to find more planets in the radius valley. And they actually predicted particular signs of this process, which is that the profile of super-Earth to mini-Neptune planets, which is determined by rates of mass loss, will be significantly different, not based on stellar type, which is what I've been paying attention to regarding thermal mass loss, but to the number of planets in the system. And this is coming back to that laminar versus turbulent flow. A system that has 3 or more planets packed in close to the star is not going to have undergone a lot of giant impact collisions, because those would just knock planets out of those tightly packed orbits. So this is a dynamically cooler disk where things aren't colliding with each other that much, which means less impact-driven mass loss, so we expect multi-planet systems to have more mini-Neptunes compared with single-planet systems. So that's a very interesting result, and you can see that here, probability that an observed planet has an atmosphere. For systems of 3 or more planets, photoevaporation, for various reasons, you expect to see fewer planets with atmospheres. With giant impacts, you expect to see a lot more. So that's a very interesting result. Should be pretty easy to see. And I'm excited to see if people can disentangle that signature from the known planet population. And finally, we had one interesting speculative type paper last month. Moon packing around an Earth mass planet. And this is simply asking the question, how many large moons can an Earth-sized planet have gravitationally? Now, we're pretty sure our own moon formed by a giant impact. And it's unlikely that there would be more than one giant impact affecting a planet during formation. And even if it did, it's even less likely that an existing moon would survive that interaction. It would either collide with one of the planets or get kicked off into space. I have seen models of moon formation that suggest that for an impact with different parameters, you could get two moons out of it. But the question here is not about giant impacts, but about gravitational stability. If you try to fit multiple large moons around an Earth mass planet, will they have stable orbits, or will interactions kick one out of the system? And this team ran n-body simulations to see how many moons of various sizes they could fit. And they came up with fancy plots like this, which are tracking orbital elements over time. And the results were, yes, in fact, surprisingly many moons can fit around an Earth mass planet. Up to 7, plus or minus 1, Ceres mass moons, 4 Pluto mass moons, and 3 moons the size of our own moon could theoretically fit in stable orbits around the Earth. Now, that's neglecting tidal migration. If you add in tidal migration, you probably want to subtract 1 from those numbers. But theoretically, an Earth-sized planet could support a surprisingly large number of moons. Whether we'll actually find anything like that remains to be seen, although, as I always say, about the only thing we haven't found regarding exoplanets is the thing we originally expected to find, so it wouldn't surprise me if there are more surprises out there.